let's get it going. Let's go live. Hello, hello. Sweet. So, what's up, stream? Hello, welcome back. Said I was gonna stream for like an hour and then be on my way. So, kind of slowly grinding through these problems, but I think that's okay. I think it's okay. So, still have another like 90 problems left. That's alright. Slow and steady. I think it's fine. Right function returns the first x number of prime numbers. So the sieve of Eratosthenes looks something like this. We'll do it. Write it in here. Sieve of Eratosthenes. The way it works is you have a list of numbers, right? And what you're going to do is you're going to iterate through this list of numbers by taking each prime number starting with 2 and removing all of the numbers, or marking all of the numbers as not prime that are multiples of 2. And then you get to go to the next number that's not marked, and you say, okay, now mark all of the numbers that are multiples of 3 as not prime, and then go to the next value that's prime. And now 4 would be marked, so you skip it. So you go to 5, and you mark all of the multiples of 5 in the range. And that's the sieve of Eratosthenes. And it's an interesting algorithm. Tricky thing about it, though, is you have to know how far out your function needs to go in terms of the prime numbers to actually have a point to stop at. I suppose you could implement it in a little more clever way by considering building a set of divisors, and you skip. Well, yeah, I mean, I guess that's sort of the classic way, is that you build a set of divisors and you iterate through each number and check, is that number divisible by any of the prime numbers you already see? If it is, then it's not prime. If it isn't, then it is prime. And add it to your set and go to the next number. You can do it that way too, building the set of primes. That's viable as well. I'm not sure if that's the same thing as the sieve. It's not quite the same, because you'll need to loop through all of the primes you've already gathered at each iteration, at each point. So it kind of slows down quite a bit over time. And there isn't really a particularly efficient way to do that. I guess it's a sort of quadratic time complexity, I suppose. Yeah, it's not particularly efficient. You could do it that way too if you don't know how many prime numbers you want. Alternatively, what you could do, you could use this sieve of Eratosthenes and use a binary search kind of an algorithm, where you take maybe the first 1,000 numbers, and see if you have enough primes in there, right? Perform the sieve and maintain the list of primes as you go, right? And then what you can do is append another 1,000 numbers to the range or whatever, or double the range of numbers that you're considering, and then apply all of the prime numbers you've already seen to that new portion of the range, the new set of numbers, and then continue from there. Continue the algorithm. I think that works too. Yeah, that's one way you can do. Yeah, you can increase how far you're going out in order to get more and more numbers. So getting the first 100 numbers for our prime numbers. Yeah. Yeah. There are a few ways to do this. Also, yeah. A few ways to do this. I'm not sure I want to code up all of that. Kind of just want to write the sieve for like, I don't know. I can like just square the input here and use that as the sieve. That should be enough. It's not particularly efficient, but it's good enough for these test cases, and knowing that there are better ways to do this, I think is enough. I think it's fine. So let's try to write a sieve. Sieve, and we'll take range, or just x or n, something like that. And then what we're going to do is I wonder if there's a way to do this functionally, like iteratively. Not really, no. Like I was thinking about like, no. The idea was like, you know, each iteration you could add another condition that needs to be checked. Each time you actually see a prime number, if it's not a prime number, then you don't need to add more conditions to check. Like you could do like just a regular prime search iteratively that way, I suppose, using like a lazy sequence, but it's not really much more efficient. It's not really that great. So here though we can say it's really like 2 loops, and now how would you do this in idiomatic clojure, so to speak? Because I know how I would do this in like C++, right? I would just have 2 loops. One loop marks all of the values off, the next loop finds the next prime, and you keep looping until I hits the end of your range, right? The outer loop hits the end of your range. No, excuse me, actually the marking also decides whether or not to update the prime value that you're working with. Change it to the next prime value that I keep checking with. So really it's just 1 loop. No, it's not 1 loop, it's 2 loops. I take that back. No. Inner loop marks everything, and the next loop finds the next prime number. So we can write a routine, so we could do it this way. We could say let do something like this. Let's say like next prime, or get prime, and this would be a function. And what this would do is take the hash map, the map, and the index, and I suppose we keep incrementing through the indices. and it's sort of a while loop kind of deal. Yeah, you could do reduce, simple enough. How far do you reduce though? It's like a certain point where you stop. There was something else too. Performing, when I was thinking about doing binary search, you could just do it recursively. Like it's not, it's fine, I think. You can do this recursively, this function, I think. Just throw recur in there. And same map ink of I. And this is as simple as an if statement. So if could do it this way, I guess. So we're gonna have if get from mi, or just mi, really should be. It's gonna be going to be a hash map, I think. Well, we kind of want an array. Really, a vector should be this thing. A vector. M of I. So we get M of I nil, I guess is what we get otherwise. And what we're gonna do is say, if you find, it shouldn't really be nil. Anyway, it'll be true or false what we get from M of I. If it's true, then return M of I. Right, which is a when, right? It's really like this, when. And there's an otherwise, right? That's really what I want. Is there a when and a when else kind of thing? I'm not sure if there's an, I think I need to have the if then else going on here. I don't think I can do it otherwise. Yeah, never mind. So if this is true, then we're going to return the value, or just I. Otherwise, we recurse. We actually want the prime number though, which is what is there. Yeah. So get prime, and then we say the sieve function. Sieve is as simple as a similarly defined thing. We just say given this map of I, let's say and there's this P, right? MIP. We're going to associate with M of I value would be the m of I is false. Alright, mark it as false, and then recur on add I with P. Yeah, and this should start at 0 when you call it. And you say if there's a problem here. Yeah, we can do this here. So if let's do condition. I don't want to do a condition. That's not what I want to do. So if I is greater than the count, greater than equal to the count of m, then we return. Then we can continue with this. Otherwise, return nil. Alright, you gotta guard this with at least one. It's also gotta be guarded here too. Yeah. I don't know what this if is here. It's actually just that's it. Like you just you should do both of these things though. Yeah. So otherwise you just stop once you get past this. And then here you say you can guard here and then say if it's true, return that value, otherwise recurse. And if you're not guarded, you don't do anything, just stop. And so what you're going to want to do, map over the range interleave range of n times n, we'll call it, and interleave that with false. constantly false, which I believe constantly gives you a lazy sequence. Repeatedly is what I want, not constantly. Repeatedly. Almost certainly. And then we want to into, alright, hopefully that works correctly. I want to start with that. And I want to say initial init map or init sieve. Okay. Okay. So now what we want to do is say, okay, we have this initial sieve, and we want to get prime and then sieve. Get prime of init sieve of I. Let's say here we just get the prime number. Here we return. Oh, this is kind of awkward, isn't it? It's very awkward. Yeah, okay. Doing things functionally, not used to it, man. You have to actually return the map at some point. In fact, what you return here is M. So you get the resulting map after you sieved. Right, you gotta actually do that. Because these are what do they call that? It's functional programming. These are persistent data structures here. So yeah, you've got to actually return the map. The thing that's interesting is you call this function, you recurse, and then return M. This M will be, I think, the resulting sieve after you've applied these changes. So you get prime, init sieve. So what you want to do, I guess the way you would do it imperatively is you would initialize the sieve, then get prime, and also, yeah, get prime starting with, actually two things. You want to return the prime itself and the index you stopped at. Yeah, I think so. Yeah. And then sieve, you're going to want to sieve from the next index with p. The thing is, you're going to want to iterate repeatedly until iterate repeatedly until get prime returns null. That's really what you want. Or nil. And each time you call get prime, you want to put that into a return value, return set. I think you want to reduce, but how do you reduce? Maybe you want to use or process sieve, update sieve. Thing is, I probably wanted to recur on this as well in order to because I need to loop, right? I could loop the reduce, but this is kind of a variadic looping that we're going to do. I don't remember if there's a better way to do this. Also, kind of variable looping structure. Returning early, I guess. Not necessarily tail recursion, but just simple recursion. I mean, you could do simple recursion too. It's not really an issue. Yeah, I guess. Yeah, I mean, we could just recur on this as well. You can use one or the other, right? If you recur at the end, then you end up with tail optimization. But if you don't recur at the end, then you just have simple recursion, which is fine. I mean, it's okay. We can do simple recursion and still sort of operate here. I wanted to use Y combinators at some point for some reason, but the more I think about it, it's like, is that really necessary? Like, I don't know, do people actually do that in their code? Y combinator in Clojure. Like, is there... Why not? Y Clojure. I got that. That's fine. Like, why would you use it though? Like, I don't think you actually need to use Y Combinator for anything. Recursive memoization. Recursive functions without using names. Many articles have been written about the Y Combinator, particularly current articles that you, the reader, are going to feel the magic with your hand. Live and interactive, powered by the Eclipse plugin. So much power in 83 characters. Factorial. Recursive call is going to be parameterized like this. It's time for magic. Exactly the same code without names, replacing Y and factorial gen with their bodies. Take the time to play with the code above, modify the values, rename the arguments. Contemplate amazing piece of code. 2 options. Practical application of the Y Combinator. Their own recursive function without names. Real life application of the Y Combinator. Okay, so basically Y Combinator is like not, doesn't really matter almost. Real life application, okay. Memoization of a recursive function. Seems easy, especially in Clojure with the memoize function. Indeed, subsequent calls are cached. Numbers only printed once, but by the way, all the code snippets of this live interactive. Subsequent calls with smaller numbers likely to be cached, but they're not. Here's the proof. Reasons that the code factorial and not factorial memo Clojure, we could modify the code of factorial so if it calls. It's very, very ugly. The code of the recursive function has to be aware of its memoizer. Use of undeclared variable. Can solve this with elegance. Okay. So it's not that practical, is it? Because like it's pretty funny. Okay, so basically you can just throw in a memoize value to your function. So I guess that's a what do they call that? That is a higher order function, memoize. So you could just memoize your functions with relative ease in Clojure. Nice. Okay. I was wondering how I was going to do that, like solving problems that have dynamic programming solutions. Right? How I can do that in Clojure. Memoize does the trick. Practical applications. Gentle introduction. Oh, do you really need this though? I feel like it's not really that useful. I've seen that though, the logging between like recursive calls, if you really want to do that. You can create wrappers for your functions. I guess that's kind of cool. So you can use combinators to add logging into your functions, I guess. That's kind of cool. and then memoizing. But you can memoize anyway, right? You don't actually need transparently interpose memoization. I'm not sure if it really matters that much. Atoms. What do we know about memoize for? Yeah, okay. Yeah. 70 days ago. Clojure is by far the best programming language I've ever used. Huh. Witness the sheer chutzpah. The guy who basically told Ruby devs they were doing it wrong, doing it all wrong at Rails conference in 2012. Oh, it's too funny, man. Interesting. It's a lot of fun, but for big projects, I guess not so much, really. Doesn't like dynamic typing. My coworkers is telling me he doesn't like dynamic typing as well. Spec asserts type hints and comments just to keep everything straight. Interesting. Yeah, I'd say that is a consideration in it. Statically typed languages. I've been like, I don't know, put a lot of effort into learning about functional programming, but I feel like it's kind of a waste of time. Like, what am I actually gaining from all this? There's pros and cons all over the place. It seems like there's not that many pros and kind of a lot of cons. It's a foot gun in large systems. I was hoping large systems would be easier to write in functional programming language. Spec helps somewhat. Primitive values for complex nested structures. Doesn't do much. Data moves to the system grows. It becomes increasingly difficult to track the mutations to the underlying structures. Do you think the static analysis tool would be some help, some sort of tooling to better handle tree structures would be handy? I often find myself being off by one level with getting calls on the tree data. Just annoying. MP gets thrown 3 function calls up the stack. Wrote a library to deal with the cognitive load and work on shapes of data. Asherize. Not saying you're holding it wrong, but maybe once you're more than a few couple levels deep into a nested map, it's time to look at it in memory database. Data script. Data log queries can replace getted vectors growing out of hand. You can also get better mutation of transactions. How long have you been programming professionally? Oof. Dynamic. Statically typed. Clojure requires more fundamental programming intuition experience to stay in larger projects. Tens of thousands of Clojure LSC. I don't feel these issues and can't relate them with Clojure. Curious to understand what the context best applies to. Wouldn't want to force out a team that wouldn't benefit from it, so I'm interested about learning these aspects. Oh, interesting. Okay. Thinks maybe it's a lack of experience. 12-ish years. Lots of got to tinker with better type systems. So I'm a Clojure developer and have been using it on and off since summer '09, using it for a large project now. Clojure, less sold as dynamic typing. Spec helps a little. Property-based generative tests helps a little too. Replace proper static types though, especially in the MLS type system with type inference. Bonus points of spec validation capacity type data to the compiler. Dream of statically type closure and type inference, spec invert types, and adoption of data type and rough experimentation glue code. Thanks for answering. Can I ask what kind of project it is? Just lucky that it fits my use case. Distribute systems of all kinds. There's tens of thousands of lines of code. Components have very strong boundaries because it's a set of services assembled together through RPC, pub subs, and DBs. What do they call that? This is distributed services, right? Distributed microservices. Microservices. Alleviate the lack of a static type checker. 3 years ago, if you believe in join, only one person knew Clojure. Stacked about 50% Clojure, 40% Java, 10% Scala. It's given us the least issues. It's just been pretty easy to maintain, generally fewer defects. Tend to have the most bugs, almost always related to some shared state. Find the hardest to extend and maintain, but the code we have for it, I think, does Scala wrong. It's like the worst mix of object-oriented programming and functional programming. Dream of statically typed Clojure with type inference. It's pretty much exactly core.typed. Interesting. That said, the project never managed to get more contributors. For typed Lisp, keeping my eyes out on Carp. Start up entirely on Clojure script. Type definitions would be difficult, I guess. It's too heavy. I guess I'm scratching my head, man. I'm gonna end up with like, I already have scabs all over my head and my face. Methods of bad ergonomics. Adding types back to it almost kills the data-oriented style. A lot like modeling with classes instead. Haskell's wiki section on this problem. Heterogeneous collections. They haven't solved it and have multiple ways to possibly handle the scenario, and none are ideal. Makes exact same decisions and trade-offs as Clojure, except on dynamic versus static types. Caveat that the development experience would be the same, the programming ergonomics and styles would be retained, and this, I'm afraid, is an open problem that no one has solved yet. And it's not just a case of personal preference. Having a language which has the pros of Clojure, pros of static types without the cons of static types is hard. That's why, for now, you need to choose one or the other. Interesting. Yeah, but it becomes prohibitively expensive if you can't understand new types. I think the problem is a monolithic programs, right? If you're using monolithic programs, then you're going to struggle. Someone had suggested using a database, which I think is correct. This talk is good. All right. 9 years of Clojure. Unicorn status, principal, practical language. All right. Okay. Enough of this. Really, Walmart Labs. Huh. Interesting. All right. Anyway, we'll continue here. I forgot what I was even doing. Prime numbers. Yeah. Right. Don't actually need to use Y Combinator for this. Bottom line. Right. So we can create the sieve initially. What's the algorithm going to work? How is it going to work? It create the sieve. Get the first prime. Update the sieve. Get the next prime. Update the sieve. Get the next prime. Repeat until the get prime returns nil, and each time you get a prime, push that into the. So we can use a reduce, but I don't really want to use a reduce as much as I want. Yeah, we can do like execute or something here, and sieve, or however they call that. When you're running simulate sieve, something like this. And this function could be recursive. And this basically, I don't think it needs an input, right, at all. I mean, yeah, if we're going to init the sieve and then simulate the sieve, and yeah, okay. I'm not sure, do we need names if we're going to recur also? That's a question. I may need to name these functions. I don't know if it matters, but what you can do is init your sieve, and no, let's do it this way. Simulate sieve. Let's take as a function the initial sieve. Or the current sieve state, I guess. M, right? And what we're going to do is get prime. And there's this I is the sort of the position we were in. So get prime of M of I, right? This is a prime. This returns 2 values, which is you may want to use a let and destructure this even potentially. We'll hold on to that for a minute, and then we want to update the sieve. Right. Could use a let, I guess. Could try that out. See what that looks like. Some destructuring here. Will be the P, and I'll just call it new I. I don't know what to call it exactly. Yeah, destructure here. And then what we want to do is update our sieve, which returns a map. And we want to use now this get prime. Yeah, it doesn't update the map at all. It's the same map. and we want to use I, which is this new I, and P. So this updated sieve. Now this we're going to return. Now we want to recur, I think. This, now we want to say something like if get prime. So we have an otherwise here. If that says, so we're going to return here nil nil, right? P and new I, these should be integers. So we say if P then if not P, I guess. Hopefully that works. If not P, then we return, well, yeah, okay, we could do that too. There's a ret here. If not P, then we just return ret. That's all we need, right? It's just not even, yeah, okay, that's fine. Otherwise, you're going to recurse with an updated sieve using the new index and the new prime number, and I think new I as well, right? Yeah, I think that's fine, although we can increment that even, because you get this prime value, right? I is the index of that prime, if there is a prime at all. If there's no prime, then you're done and return what ret has inside. Otherwise, you're going to recurse on by updating the sieve, starting this new I position, which is exactly now. You actually want to use. You actually want to bind a new I to itself incremented by 1, I think, which is a bit strange. Yeah. Yeah, I think, I don't know, do I really want to, do I do it here or do I want to do it here? I probably want to do it here. I think this makes more sense because this is where the ith, this is where you found the prime number, and this has got to be, you know, then whatever you want to do with it afterwards. So here we can just say new I is inc of new I. Somewhat imperative doing it this way, but I think it's okay. And then we update the sieve with m new I of p. We don't need to increment new I anymore here. And yeah, ret is just associate or just conj ret with p, and that's it. And recur with that. Kind of simple. Kind of simple after all. Why doesn't this? Oh, okay. Yeah, and so we're going to return the simulate sieve with init sieve I probably starts at, so if it's going to be range 0 to n squared, we want 0 to n squared would look like what? We don't care to start our primes at 0 or 1, 2. I think is where we want to start the prime index 2. Yeah. And map 2 and ret. It's got to be empty initially. And that's it. That's the whole shindig, man. Now let's see how we do. Oh, and we can take whatever n is, and we can take, you know, just take n of these. Take the first n. Alright, let's see. Compiling too few arguments to if. Interesting. Which one? It's 929. Really? $19.29. Is it this one? Which one is it? It's got too many, not too few arguments. I feel like it takes a really long time to program in Clojure, or at least it does for me. Maybe it's just me. It could just be me. Too few arguments to if. Like, what if we just return m? Right? Like, what if we do that? Same error. Yeah. Okay. So this is the problem. But this has two things, right? There's recurs here. Oh, that might be the problem. Ah, that's why. No, this, I don't know how I managed to miss that. Got it. That makes sense now. Okay, understood. Okay. Let's get that REPL going. Count to recur, expected 3 arguments, got 2. Oh, of course. Time for bed. What do we want? We want 100 in the last. Let's see how we do here. Come on, man. What about sieve of like 5 or something, you know? Boolean cannot be cast to a function. Ouch. Man. Yeah, I want to say P, not P. think it's this one that's which one is this actually? I don't know what the problem is. Also, we can that's not what I wanted. Let's do like 25 or something, or 5 by 5. Oh, interesting. Huh. Really? Found the error. Okay. Could we just like take 5 or something? What is going on? Boolean cannot be cast to a function? What? Repeatedly. Oh, is that what I think? Oh, I think I know what's happening. Ah, I see. I don't use this too often. It's repeatedly. It takes a function. Repeat is probably what I want then. Yeah. Okay. Got it. Repeatedly is takes a function and executes the function repeatedly. Repeat, on the other hand, is what we want. Zero, false, 1, false, 2. Oh, that's not what we want either. I mean, it's kind of what we want, but it's not really, not exactly what we want. Yeah, okay. And also, I think it should be true initially. Yeah, the way the maps work, this actually would be... Oh, come on. What? What? I think it's an apply we want. I think it's the other way around we want. Yeah, I don't want that. I want... It's a little confusing here. It's a little confusing. I think this is what we want. Oh, okay. Let's do 5 by 5. There we go. Sweet. It's all over the place. Look at that. Nice hash. That hash though. Sweet. Okay. I can try again. Oh. Come on, man. Come on, man. Boolean cannot be cast to number CLJ 9. Oh, this is killing me, man. What? Where is the... What's going on here? Okay. So if we execute sieve of 5, right? What happens? What happens and why? Class cast exception. Okay. Boolean Boolean cannot be cast to class Java lang number. Module Java base of loader bootstrap. Boolean to number. Yeah, but where is that happening? Is this it? Is this the problem? Have we just said true here? Would that be the end of it? It is. That is the problem. Nice. Alright, you could just say if p equals nil, then return. Otherwise, see what happens here. You gotta be kidding me. What is going on here? Where is this happening? When is this happening? This exception. Excuse me. Can we just print here? This is a compilation error? No, it's a... Yeah, it's a runtime error. Oh, wow. So it runs a whole bunch. And then we hit here. Alright. Excuse me. Let's see what happens. Oh, P is true all the way through. It's just true. What is P? Whoa. That's not what we're supposed to be returning. No, definitely not. No, 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 no. It's just true. That's not correct. P is supposed to be an integer. Oh. Oh, that's why. Ah. I see the problem. Oh, that's confusing as heck. Actually, I is both the index and the prime number. Right. Oh. I see. Right. About that. Yeah. That changes things. So that was my logic that was off. Oh. Oh. Let's see. See the problem. Did I just crash my my shell? Yeah, I think it crashed the shell. So this went into an infinite loop, huh? How do you increment nil? Also, this is nil, which you can get sometimes. I don't know what just happened. 425. P, right. Recur the last time. Update sieve, I think is nil. Get prime is nil. Count of nil. Right. Okay. Interesting. Excuse me. I don't get it, man. I don't know what's going on. This has a base case, right? Like it does. You get 25, 24, 25, right? That's P. And then that's not correct though, right? Like P should change to, you get prime M of I, get this new I, recur. Shouldn't this be a little confused? I don't think this is recurring as expected. It's definitely not, right? Right. Oh, yeah, we're printing P at each point. P is not changing to different prime values at all. M of I, if I is less than the count of M of I is nil. Recur M of increment I. Can we just print I here? Just see what happens here. Okay, so I is just the same thing every time. Really doesn't change much. Okay, yeah, that's fine. That's not really what we're trying to do here. It's a little confusing. So, swap recur and nil. That way it's genuinely the last line. I don't think that really matters though. I don't know, just call this get P. The problem is that get P is not defined here, right? So it's not gonna know. Or will it? Maybe, I don't know. What about this now? Maybe it is better after all to not use the REPL in some cases. I'm kind of falling asleep over here. This is taking so much time. Dude, I don't know if I want to be a Clojure programmer. The more that I work with it, it's like, I don't know, man. I think this feels like just a lot of getting used to. a lot of familiarity. Like, this is not doing what I want it to do at all. Not even remotely. If man, come on. Shoot. Wow. This should be false, right? Also, I just want to sleep, man. I'm tired. I'm ready for bed. I'm ready for bed. True. It just keeps returning true. Why is it true? Is everything true? There's nothing. I'm sorry. This has more to do with me not programming sieves repeatedly. Problem. Do we close this program yet? Yeah. This is looking for things that are true when oh. Huh. What? What? I have a feeling this has something to do with regardless is recursing. Kind of want to like set bindings here or something. Like a looping point, something, I don't know. Something weird's going on here. I feel like I need a loop. Feels like I need loop somewhere in here. Yeah, which I don't really want to use. I'm trying to avoid it, but I don't know. I don't know, man. So it rebinds to the function. You don't actually need to name the function, it'll recur properly, it seems. But why doesn't recur to a let, does it? I don't think so. I'm kind of confused here. So if you call init sieve, like if you call actually, no. Yeah, it's fine. I want to say if you simulate the sieve over in Itseif, just update sieve over in Itseif, right? New I and P. P could be 2 initially, and new I guess would be 3. Alright, and I just want to see what this does. What is going on? True. Yikes. So update C doesn't do anything. Interesting. Well, that's not good. That's not good at all. What? What? I is less than count of M. What in the Sam Hill? 25. Okay, that's expecting that. Now why? This is so I is right. So this is true. Oh my goodness. That's why. Okay. Logic. Good old logic. Okay. Nice. There we go. Alright, let's see what happens now. Probably don't need to print all these lines, but maybe we'll leave it just to see. Alright, small improvement. 2 true, check. 2 3 3 false. True, check, false. So check P new I. Where'd that 2 come from? Oh, these. Get rid of these. I think I can put this back to recur as well. One more time. See what happens here. Okay, check 2 3, check 4 5. Interesting. No. Oh no. Ouch. That's a problem. Yes, that's a problem. Okay, I see. No. I mean, this can work, I guess. That's fine. It's just kind of messes up the array, doesn't it? Yeah, that's interesting. Okay. Yeah, this will make some sense, I guess, after we run it. Also some syntax error here. Oh, done. Nice. Got him. 2, 3, 5, 7, 11, 13, 19, 17, 19, 23, nil. Cool. Yeah. Okay. Oh my goodness, man. 1, 2, 3, 4, 5. There you go. All right. All right. Sweet. So that looks like what we want. So we sieve. Oh, we don't have to do that. Yeah. You do it the other way around. You could take from the sieve, I guess. But, do it this way. I'll take n from the sieve after result. So we sieve. Oh, we don't want that. Cool. 541. Ooh. Oh, it is. Okay. Neato. So let's save this. Move this back. Copy. Paste. Run. Undo, undo. Nice. Holy smokes, man. That took forever. I mean, we're learning a lot, right? I mean, if we really want to be good at Clojure, quote unquote good, want to get good, need practice, need to get familiar. Ain't no other way. I don't know, man. I don't know. Let's see the solutions. No, I'm afraid to look at the solutions, man. Oh yeah, this is so simple, the GCD. Although they didn't include a check in case A is larger than B. Kind of need something in there. The subtraction. There's the greater than. GCD. Nice. Whoa. Interesting solutions. Would have been cool to implement binary GCD. That would have been interesting. Alright, here's my here's my sieve. Holy smokes. Jeez. Oh wow, someone else had a much simpler way to sieve. Range, drop to, filter, not any. Well, these are not really like, these are like brute force. Oh, that's pretty good. This is sieve. Could look at these later, I think. Kind of don't want to look at these. I don't want to go to bed now. I'm tired. Some of these are sieves, and some of these are just like check directly if it's prime or not. Come on, man. All right. Okay. Yeah, I don't know. The ones that are like just not even implementing the sieve is kind of meh. Probable prime. Whoa. Whoa. Java is probable prime, huh? Probably prime. Probable prime. Check that out. Check that out. Some explanations for this, huh? Large known prime for any uncertainty greater than 0. Is it accurate to say? Documentation says it will turn false only if it is certain the number is composite. Turns true if it's probably prime, false if it's definitely composite. Large known prime. So what does it implement? This is probably it probably uses what do they call that? There's a name for this. Probably uses fast primality checks. There's like pretty special primality check algorithms. Probably use the fast ones, the special ones. Pretty cool. Neat. Kind of curious what it's implemented in, but I'm not gonna. Recur, throw. Yeah, we're looking at that. I thought maybe I misprogrammed it. I thought maybe I did something, or I misunderstood how the recur works, but my logic was nonsensical. What is this going on, man? What is this? You gotta be kidding me. Oh boy, that's very funny. Wow. 1999, do start 2010. Any 64-bit input. I guess if you need like super high performance, you can use this, which is basically like a fancy way, like it's kind of like a hash map of all the values, but there's a lot of them, so you want to use something a little bit better than just a hash map. That's effectively what this is. That's pretty funny. What is that, man? Come on. Come on. Infike solution. Previous primes, decrement n. interesting. Primes recur. I feel like I should read these, so I'll come back to these. I'm just kind of like browsing here. Yeah, I should definitely like read each of these. Some of these are pretty funny. We'll come back to this later. I want to go to bed now. So yeah, thank you for hanging out, saying hello. I do appreciate it. I don't know if anybody did come by and say hi. Well, either way, thank you for watching. Talk to you all soon. Have a good rest of your night. Take care.